Okay, good morning. Okay, but do you still remember what we have already learned 2 weeks ago? Like a basic set theories. We also learned the probability model. Okay, and today we're going to talk about the Bayes theory, and then later on we will move to the discrete random variable. Okay, so first, what is the Bayes theory? I have two events, A and B, and the probability of A and also probability of B is greater than 0. In that case, then this equation holds. Probability of A given B, the event B, times the probability of event B, they'll be equal to the probability of B given A, the conditional probability, times the probability of A. Let's quickly prove this. So probability of A given B. By the definition, the conditional probability, that is probability of A intersect B divided by probability of B. And we know probability of B given A will be probability of B intersect A divided by probability of A. So in this case, see the right hand side, probability of A intersect B. Here I have a probability of B intersect A. They are the same. So since they are the same, the left hand side times their denominator will be also the same. So probability of A given B times probability of B will equal to probability of B given A, probability of A. Next is the total probability. Also based on the Bayes theory, what is the total probability? If B is an event and A1 to AN are the partition of the omega, the universal set. What does that mean? A1 to AN are partition. So the partition means they are disjoint. Each of their events are disjoint. So if they intersect different event, they are disjoint. Oh, no, sorry. The intersection of two events will be an empty set. And also, if I union all the events, suppose we have n events, then it becomes a universal set. That will be the partition. So if it is partition, then what is the probability of B? The probability of B will be the conditional probability B given on one event AJ times their corresponding probability AJ, and then I sum them together. Let's also can quickly prove this. So the summation probability of B given AJ, probability times probability AJ. You may think about this as conditional probability will be probability of B intersect AJ. And then J is from 1 to N. And then this equals the probability of the union B intersect AJ, and J is from 1 to n. So here we use axiom. Okay, so where's the axiom? If they are disjoint, the summation of the probability will be the probability of the union. And here we can also simplify it. That will be probability of B intersect the union of A from J equals 1 to J to n. And then we still have a space, so maybe here. That will be probability of B intersect the universal set. That is probability B. Okay, so later on we will use the total probability and also the Bayes theory in the future. So now let's see an example. For this example, consider this typical communication channel. Okay, for this channel, a source transmits a string of binary symbols through this noisy communication channel. And it's either 0 or 1 with the probability P. If I send 0, that is the probability P. And I have probability 1 minus P to send 1. And then I will receive incorrectly with the probability epsilon naught or epsilon 1, which means that if I sent 0 and then I received 1, this error probability will be epsilon naught. If I sent 1 and I received 0, that is the probability of this error will be epsilon 1. Okay. And if I send 0 and I receive 0, that is this probability will be 1 minus epsilon naught. And errors in different symbols transmissions are independent. Okay, so now I want to know S is the source and R is the receiver. What is the probability that the channel receives 1? I can send 1 and receive 1. I can also send 0 and receive 1. So what is that probability? And then given 1 is received, what is the probability that 1 is sent? Because if I receive 1, I want to know if it is from the source, I send 1 or I send 0. And then what is the probability that the symbol is correctly received? Which means if I send 0, I will get 0. If I send 1, I will get 1. Okay. So first, based on this description, okay, we can write a probability. First, probability of the source is 1. I sent 1. That probability is 1 over P. That also means if I send 0, then this probability is P. Then what does that mean that I have epsilon naught or epsilon 1? Epsilon naught means that I receive 1, but actually I sent 0. So epsilon naught means I sent 0, given that I sent 0, but I receive 1. That is epsilon naught. And also, given I sent 1, but actually I received 0. That is the probability epsilon 1. From the axiom of the probability, we know this also implies the probability I receive 0 given the source I sent is 0. That probability is 1 minus epsilon naught. In that case, the probability will be 1. And similarly, this gives us, that also says that given 1 is sent and I receive 1, that probability is 1 minus epsilon 1. Okay, so now for the first question, what is the probability that the channel receives 1? How can I receive 1? Receive 1 means that I may send 0 and I receive 1. I may send 1 and I also receive 1. Okay, so that means given 1 is sent and I receive 1. And given 1 is sent, the probability of having 1 sent, that is 1 minus p. The other situation is given 0 is sent and I receive 1. Okay, so just plug in what we have. 1 minus epsilon 1 times 1 minus p plus epsilon naught p. Now we know that the probability that the channel receives 1 is here. Then for the next question, given 1 is received, then what is the probability that 1 is sent? Because maybe 0 is sent and I still receive 1. So, and also you need to know that how to write this description into the math form. Given 1 is received, then the probability that 1 is sent. That means given 1 is received, that 1 is sent. Okay. Conditional probability. So, two events A given B. So I have A intersect B divided by probability of B. So what is A intersect B? We only have these 4 options, so we may use here. One is sent, intersect 1 is received. That is the probability of 1 is received given 1 is sent times probability of 1 is sent. And then denominator will be from part A. Then the next question, that what is the probability that the symbol is correctly received, which means that I sent 0 and I received 0, and I sent 1 and I received 1. So for the probability that is correct received, that'll be I send 1 and I receive 1. So I receive 1 intersect I send 1. Also, I sent 0 and I received 0. So here we still use the conditional probability. 1 is received given 1 is sent. So 1 is sent, the probability we also need to include. And the second part, 0 is received given 0 is sent. Times the probability that 0 is sent. Then you have 1 minus epsilon 1 times 1 minus p plus 1 minus epsilon naught times p. Okay, then let's extend the Bayes theory to the Bayes rule. Now, I have any partition A1 to AN. So, specific one event from the partition given the event B. What is the probability? Similarly, there'll be probability B given A, that event, times that probability of A. But we will divide the total probability. So we just proved this. Why here is total probability. By the definition, so AJ given B, it should be probability of AJ intersect B divided by probability of B. And we just done that probability right here. A intersect B there will be probability of B given A, that event AJ, times probability of AJ. And for the probability B, since A1 to AN are partitioned, then using the total probability law, then we have probability of B given AJ times probability of AJ. J is from 1 to N. And later on, we will use this concept in some questions, and we will see this, and then we discuss that more. Now, before we really talk about the random variable, we still need to know 1, 2, 3 more concepts. Now, this concept is called that statistical independence. Here's the definition. Two events, A and B, we call that they are independent if the probability A union intersect B will be the multiple of their individual probability, PA times PB. Then we can say A, B are independent. So first, let's see how do we interpret the independence. And here we call this is statistical independence, just compared to the linear independence that you learn from the mathematical engineering. Okay, it's a little bit different. Linear independence and statistical independent. So by Bayes' theory, we know the conditional probability A given B, there will be the probability A intersect B divided by the probability of B. But what if A and B are independent? If A and B are independent, the numerator can be replaced by the individual multiplication, probability A times probability of B. And we also assume that the probability of B is greater than 0. So, therefore, A and B are independent. Here, that means if the outcome of B provides no information or no additional information about the occurrence of A. So, it doesn't matter that how A occurs, B won't affect. So that is the independent for two events. We can also extend the independence to more than two events, 3, 4, or even 5. So if I have 3 events and we say they are independent, that means we need the mutual independence, which is also called the pairwise independence. So we need mutual or pairwise independence. What that means, I need to consider A and B first. A intersect B, this probability will be probability of A times probability of B. And how about AC? Because it's pairwise, so A intersect C. Exactly, that should be equal to probability of A times probability of C. And also, probability of B intersect C. That should be probability of B times probability of C. And then last, here. And also we need to consider the joint independence. So that means probability of A intersect B intersect C. There will be also the individual multiplication of their probability. Probability of A times probability of B times probability of C. So now let's see an example. If I roll the die twice, now I have an event. Remember that we always have to create an event, and then we say the probability of that event. What is the probability of that event? Not the outcome. So the event A is the first row is 3, and the event B is the second row is 4. Is A independent of B? To check if they are independent, we must satisfy this equation. So we need to find A intersect B. So first, what is A intersect B? The probability. So probability of A intersect B means the outcome. The first is 3 and second is 4. Okay, 3, 4. And this outcome 3, 4, for rolling the die twice, there will be 1/36. And the probability of A, the first row is 3, that's 1/6. The second row is 4, probability is also 1/6. So the probability of A intersect B will be the multiplication of probability of A times probability of B. So yes, they are independent. Then if I roll the die twice, but the event is different. Now A is the maximum of 2 rows is 2. And for the event B, minimum of 2 rows is 2. So for this event, the maximum of 2 rows is 2. How many combinations that we have for this event? The maximum row is 2. So I can have 1, 2, the second row is 2, or the first row is 2, but the second one is 1. And also that both rows are 2. Okay. The minimum of 2 rows is 2. Then in this case, the minimum is 2. So I can have 2, 2, and then 2, 3, 2, 4, 2, 5, 2, 6, 3, 2, 4, 2, 5, 2, and 6, 2. So now let's see probability of A intersect B. What is this? Only 2, 2. That'll be 1/36. Probability of A here 1, 2, 3, so 3/36. And probability of B, there will be 9 outcomes, 9/36. So apparently they are not equal. So they are not independent. So again, now when we say that A and B are independent, we say that the occurrence of B provides no additional information about the occurrence of A. Here you can see that in the example of A, the first row is 3 and the second row is 4. Actually, the second row is 4. It doesn't matter to to affect the occurrence of A, because A is the first row. That'll be 3. So they are irrelevant, so they are independent. But for the second example here, the minimum of 2 rows is 2, and the maximum of 2 rows is 2. For this 2, it really depends on each other, because when you roll the die twice, well, the first row and the second row, it really affects for both of your rows. So they are not independent. Let's see another example. Now for the real line, to find the area, I have the universal, the sample space, that is 0, 1 square. And here I have A, B, and C. Let's see. Let's draw those areas. First, for the sample space, omega, there'll be 0, 1. Where should I put? Probably just put here. Hold down the space. Yeah. Okay. It's 0, 1. So here's 1, and here's 1. Let's see. Okay, it's in this area. And for area A, x is greater than 1 over 2. It'll be 1/2, 1. And here is still 1. For A, let's use green. Okay, this area. And for B, y is greater than 1 over 2. Here's 1, and here's 1/2. 2, 1. Then let's have maybe purple. Okay, last one. For C, x is greater than y. Of orange, we still need to have 1 first. Okay. Now I want to find A intersect B. A intersect B means the probability of the xy such that A intersect B, so x should be greater than 1/2, and y is also have to be greater than 1/2. Then let's plot A intersect B. Okay, so you only have this part. Okay, let's draw it. The intersection, let me use maybe pink. Greater than 1/2. 1/2. So okay, this area. So this area compared to like 1, 1, the area is just 1/4. So that's 1/4. And we can also see the probability of A is 1/2. Probability of B is also 1/2. Okay, so this is 1, right? They only occupied half of this area. They also occupied half of this area. So probability of A intersect B is equal to probability of A times probability of B. They are independent. Let's see probability of B intersect C. That means there's the probability of xy such that B and C, y is greater than 1/2 and x is greater than y. So y is between 1/2 and x. And so let's plot B intersect C. This one is A intersect B. Here we can have B intersect C. Right, so this is B intersect C. This area is 1/8 of the total area. So this is 1/8. And then the probability B and probability C are 1/2. So the probability of B intersect C is not equal to probability of B times probability of C, which means not independent. Let's talk about the disjoint and also independence. Let's compare these two, and then we can take a break. For the disjoint and independence, we say A and B are disjoint. What does that mean? The two events, A intersect B, will be an empty set. So it is empty set. The probability of A intersect B will be the probability of an empty set. An empty set for the probability that's 0. And this does not imply that the probability is just 0. So that doesn't imply the probability A intersect B is the probability of A times probability of B. Unless probability of A is 0 or probability of B is 0. And if we say A and B are independent, that means the probability of A for A, B are independent. This also doesn't mean this does not imply probability of A intersect B is 0. It is probability A times probability B. Okay, unless probability A equals 0 or probability B is 0. I'll put 0. So, for the conclusion, can we say if two events are disjoint, that implies independent? And also, if two events are independent, does that mean that they are joint? Which is no. Okay, now let's continue. The next one is called the sequential experiment. What is a sequential experiment? We consider a sequence of experiments if each experiment is performed independently with identical procedures, like I flip the coin, or I roll the die, or I turn on the light, turn off the light. Then the sequence is said to be independent trials. So for each experiment, there are only 2 possible outcomes. So if I roll the die, no, because I have 6 outcomes. So if I only have 2 possible outcomes, then we call it Bernoulli trial. For Bernoulli trial, you only have 2 outcomes. I flip a coin, I turn on or turn off the light, and I send 0 or 1 to the channel, I only have two outcomes, either 1 or 0, on and off, head and tail. That is called Bernoulli trial. Okay, and they are independent. I do 10 times. Each time, they are independent with other trial. So if I flip 3 coins, if I flip coin 3 times, the first time I flip the coin, and my second time flip the coin, the third time I flip the coin, they are independent. So if I flip a coin 3 times, what is the probability of getting 3 heads? If I flip a coin 3 times, they are independent. Okay, so since they are independent, even though I have 3 events here, they just had the head as an event. Then I can separate each and find the probability and times together. So that'll be 1/2 times 1/2 times 1/2, and you get 1/8. And this is the Bernoulli trial. I can also flip a coin, but it's a biased coin 3 times. So if it is biased, then I need to tell you that to get in the head, the probability of getting the head is P. So probability, maybe put here, probability of getting a head is P. And now I will say K is the numbers of heads. So if I flip the coin the first time, I'll get either head or tail. So it's either head or tail. My second time, it's also either head and tail. Either head and tail. Third time, also head and tail. Okay, so you get the probability of getting head is P. So here is P. That means getting the tail, there'll be 1 minus P. So when you get the head, then that probability is P. Getting the tail, the probability is 1 over P. So now, after you draw this branch, then here you get 3 heads. 3 heads. Then the probability is P cubed. Here you have 2 heads and 1 tail. This probability is P p squared times 1 minus p. Or we get head, tail, head. It's still 2 heads and 1 tail. So that probability is still p squared times 1 minus p. And then you have head, tail, tail. So the probability is p times 1 minus p squared. In the following case, I have tail, head, head. So the probability is p squared times 1 minus p. And then I have tail, head, tail. So I have 2 tails and 1 head. So that is p times 1 minus p squared. And then I have tail, tail, head. The probability is p times 1 minus p squared. And the last one, all tails. So the probability is 1 minus p cubed. So probability of having just 0 head, that will be 1 minus p cubed. Probability of getting 1 head, that's 3 times 1 minus p squared p. 2 heads, that will be 3 times 1 minus p squared. And you have 3 heads, p cubed. Okay, the next will be binomial probability law. And what is binomial probability law? I consider a sequence of n independent Bernoulli trials. So for the Bernoulli trials, I flip the coins n times. I turn on the light n times, or I send 0 or 1 to the channels n times. And that k be the number of successes, then the probability of getting k. So k successes in n Bernoulli trials, that will be n choose k times the probability p to the k and 1 minus p to the n minus k. So like I flip the coins, so it's either head or tail, then I would like to know the probability of getting 3 heads or 5 heads in 10 Bernoulli trials, in 10 tossing. Then what is the probability? So here we have to know for this probability n choose k, p to the k times 1 minus p to the n minus k. Here we have a binomial theory. The binomial theory means like a plus b to the n is in this form, the summation form. For this summation form, if I choose a as p and b as 1 minus p, then let's see what happens. Because p and 1 minus p on the left hand side, there will be 1. So if I choose a equals p and b equals 1 minus p, then 1 to the n will be still n choose k, p to the k times 1 minus p to the n minus k. So you can see that if I do the summation, consider all situations for the k, then the overall there will be 1. So for example, if I flip a biased coin 3 times and the probability of getting 2 heads, to getting two heads should be 3 times 1 minus p times p squared. But according to the binomial probability law, we can also have a double check. Probability of k equals 2. That means there'll be 3 choose 2. And p to the 2 times 1 minus p, 3 minus 2. So 3 choose 2 means 3 factorial divided by 2 factorial times 3 minus 2 factorial, p squared 1 minus p, and that equals 3 times, I still write p first, p squared 1 minus p. So same answer. Now, if you don't have any questions, then we have already known all the basic knowledge. Then we can talk about what discrete random variables are. So what is the discrete random variable? First, let's flip the coin 3 times. To flip the coin 3 times, what is the possible outcomes? And we collect the possible outcomes together to form the sample space. So the possible outcomes will be 3 heads, 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 or heads, heads, tail, or head, tail, head, tail, head, 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 tail, tail, and tail, head, tail, 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 head, and finally tail, tail, tail. Now, and that the x is a number of heads. So what does that mean? Probability of x equals 2. And also you may think that what is the meaning of x equals 2? X is the number of heads. Okay. So to answer those questions, first let's see that C be one of the 8 outcomes. So we have 8 outcomes here. Okay, so C is one of the 8 outcomes, say head, head, and tail. Then x is number of heads. X actually is a function that maps this C to a value, right? Because we say x equals 2. So I just map this possible outcomes. I have head, head, tail. I have 2 heads, okay, to a value 2. So for every outcome, C, these 8 possible outcomes, we can also assign a number. For example, for C, we have 3 heads, then I will assign this C to 3, number 3. If it is 2 heads and 1 tail, then I assign the C, the outcome, one of the 8 outcomes, to number 2. Similarly, for head, tail, head, then I assign the C to the number 2. And tail, head, head, also number 2. But if I have head, tail, tail, I only have 1 head, then I assign C to 1. So this C could be different numbers. We just map the C to a value. So we call this function x. We map the sample space to the real line, a random variable. So I just assigned the outcomes to a number. And to map the outcome to the number, this function is called random variable. So what is a random variable? Actually, the random variable is a function. Okay, even though the name is called variable, but it is a function that maps an outcome to the sample space. Maps the outcome in the sample space to the real line, to the number on the real line. So if I have a sample space here, this is sample space. So sample space S, I have the outcomes. Say this is C1, one of the outcomes. Here I have another outcomes, and then I'll map the outcome to a number on the real line. So I may map C1 to X C1. That'll be a number. 2 will be here, C2, and then for C3, I also map C3 to a number on the real line. So now by this definition and this example, now here are some notes. X, this is called the random variable. Actually, it is a function. So the random variable is a function. And this function is to map your outcome on the sample space, in the sample space, to a number on the real line. And the C is a random outcome of an experiment. When you roll the die, you'll get either 1, 2, 3, 4, 5, or 6. When you flip the coin, you get either head or tail. If you just turn on or turn off the light, you just turn on or turn off. Okay, if you draw a ball from an urn, then you may get different colors. Those are the random outcome. Then if I have this function x and also the random outcome, if I combine that together, x of C, what does that mean? X of C. X of C, there will be a particular value, value of x at a given outcome. At a given outcome. So here you can see a particular value. So it is a value. So the value is either like 3, 2, or 1 for flip a coins 3 times. And see the notation that we have the capital X, that is a random variable. Then how about the lowercase x? What is a lowercase x? The lowercase x is a generic real number. So you may see like x, the random variable, is less than or equal to a specific number. This is just a real number. This means a c such that if I map the c to the real line, it should be less than or equal to some number x. Okay, so for example, if I flip the coin 3 times, what does that mean? X is less than or equal to 2. That means the c, one of the possible outcomes, such that if I map this outcome in the sample space to a real line, it should be less than or equal to 2. So if it's less than or equal to 2, then my possible outcomes will be 2 heads with 1 tail, 2 heads, 2 heads, or even 3 tails. Okay, so now the x, the capital X, is an object, and it is not a numerical value. And for this random variable x, it always has the PDF, the PMF for discrete case. Always has a PMF, and we will talk about the PMF right away. This is for discrete case. For this random variable x, it always has a different numerical values of a different experiment. Okay, if I roll the die, then the number could be 1, 2, 3, 4, 5, 6. And if I flip the coin, there'll be head and tail. But for the random variable x, as you can see from different experiment, I can flip the coin 2 times, flip the coin 3 times or 4 times. Then they will assign the possible outcomes to the real line. Then this number will be different. Because if I say that k is the numbers of heads, but if I just flip the coin 2 times, this number just could have 0, 1, 2. But if I do the 3 times, I can have 0, 1, 2, 3. If I flip the coin 4 times, so getting the heads, then I can have the number from 0 to 4. So this x has a different numerical value of a different experiment. However, for the lowercase x, it is a number, and it is a deterministic number. And for this lowercase x, it is a particular outcome. And we also call it a random realization. Okay, so now let's see the definition. we call that a random variable x is discrete if the range of x contains a countable number of elements x1, x2 to infinity. So it's countable. And a discrete random variable x is finite if the range of x contains a number of finite elements. Like if I roll the die, then I only can get 1, 2, 3, 4, 5, 6. Okay, so that is finite. And then, what is the probability mass function? Each time, from now, each time when you learn the different type of random variables, then we need to know their probability mass function for discrete case, or the probability dense function, the PDF. Okay, because the PMF or PDF can describe that variable, that discrete, that random variable. So the PMF is a function because we call it a mass function. So it is a function. That function specifies the probability of obtaining the number x equals the deterministic x. And we denote this PMF here. Okay, Px of x, you can see that now they have so many x, but don't be confused about the notation. The PMF means that the probability of your random variable x equals a certain value, some value x, which means that is the probability of your outcome, Kasi, such that if I map the Kasi to the real line, that will be equal to that number x. This is the probability mass function. So here you see that this x is the random variable. And for this x, lowercase x, this is the value. So here's the note. If you do the summation of your probability mass function, consider all possible outcomes, then there will be 1. The probability will be 1, which is reasonable, right? You need to consider that if I flip the coin, if the probability of getting head is 30%, then the probability of getting tail will be 70%. So when they add these two together, you'll get 100% for getting the tail and head, or head. So based on this concept, if I have the PMF, we say this is a valid PMF, then we need to find the constant C. How do we find the constant C? If it is a valid PMF, which means when I sum this PMF, it should be 1. Because each outcomes I have a probability, and I sum all the probability of each outcomes, this should be 1. So k from 1 to infinity, c 1/2 to the k. You get c times 1/2, 1 minus 1/2, that's 1. So in that case, C is 1. Another example, the PMF is either 0 or greater than 0. Well, not the example, there's a note. The PMF, if x is on a certain number, then it's greater than 0. Otherwise, it'll be 0. So if I plot the PMF, this is x, and here is p of x. So I have x1, x2, and x3. I only have values at x1. And here is, we say, the px at x1. And I may have values at x2, but smaller. So px equals px x1 of here sometimes you may see those notations. You may have xk and they are all equal, or you just say rather than x I have a k, or sometimes if you see some textbook they just have px, the pk. Okay, but you can see that this is the random variable, discrete random variable for x. So inside the, and also this is a function. So I can put y. This is still for the random variable x. It could be, you can put any parameters actually inside the parentheses. So you can also put like a smile face. Okay. So don't be confused about the notation. This is just the PMF for x. So now let's see an example. I flip the coin 3 times. So coin, coin flip 3 times. And x is the number of heads. So what does that mean? PMF 0. That means probability of x equals 0. And px1 means the probability of x equals 1. Here we only have these two, so this will be 1/8, and this will be 3/8. So we can also plot the PMF. My outcomes will be 0, 1, 2, 3. And the probability of getting 0 will be 1/8. Getting 1 will be 3/8. And getting 2 will be also 3/8. And getting 3 heads will be 1/8. So from the definition here, actually the PMF, the probability mass function, is the probability. Okay, you can see this definition. That is the probability of your random variable x equals that specific value x. Okay, the next, here you see that we have the probability x equals either 0, 1, 2, or 3. But sometimes you will see that probability of x is less than or equal to 2. What does that mean, that probability of x less than or equal to 2? That is also practical, right? You may want to know the probability of getting heads that's less than 2. If I flip the coin 5 times, what's the probability of getting the heads that is less than 3? Or what's the probability of getting the number less than 4 when you roll the die? So here we also have another function called cumulative distribution function, CDF. For the discrete random variable, here is the formula. This is the definition. The CDF of x is equal to the probability of your x, the random variable x, less than or equal to some certain point or some value x. And since it is a discrete random variable, so this probability, I can do the summation. For the continuous random variable, later on, we will learn that, then we will do the integration. So for this summation means that I consider all the cases that this random variable is less than or equal to that certain point, certain value. So here we have k less than or equal to x. And I will consider all these possible situations and sum them together. So if I flip the coin 3 times, first we know the PMF getting 0, that'll be 1/8. The PMF getting 1 is 3/8. Getting 2 is still 3/8. And getting 3, that'll be 1/8. So for the CDF, f of x of 0, that means this is the probability of your random variable x less than or equal to 0. Less than or equal to 0, that means I only have the PMF at 0, which is 1/8. Then the CDF of x at 1, that means the probability of your random variable x less than or equal to 1. So if x is less than or equal to 1, I include the PMF at 0 and also PMF at 1. And for the CDF at 2, that means the probability of your x is less than or equal to 2. So I will include the PMF at 0, 1, and 2. You'll get 7/8. And later on, you get the CDF at 3, which is the probability of x is less than or equal to 3. We get the PMF at 0, at 1, at 2, and also at 3. So if you plot this CDF, I have 1, 2, and 3. 1, 2, 3. And 1/8, 1/2, 7/8, and 1. So here I have 0. When x is 0, the PMF is 1/8. When x is 1, the PMF jump to 1/2. So between that, I don't have any value, so it's still 1/8. But when x equals 1, they jump to 1/2. Till x equals 2, they'll jump to 7/8. And then and they keep the same value till getting 3 heads, then I get 1. And you can observe that for this chart with CDF, here I have a gap. But for those gap, here is 1/8. And here is 3/8. And here is 3/8. And also this is 1/8. You can see that this gap, the green color, that is your PMF. We will also see this when we talk about the continuous random variables. Okay. In this example, we can observe some properties of the CDF. And these properties of the CDF is the discrete random variable. Okay. And so for those properties, you can also observe by yourself first during the break, and then we will talk about those properties. Now let's see some properties of the discrete CDF. Okay, so you can see this chart. The CDF is a sequence of increasing unit step. Okay, it is increasing and it's like a unit step. And the maximum of the CDF is always 1. Okay, because you can think about the CDF is the cumulative distribution function, and it is the probability as well. The probability of something, the random variable x less than or equal to some specific value. And since it is a possibility, it is a probability, then the maximum value is 1. And of course, the minimum value is 0. And then you can say the unit steps have the jumps. If the PMF is greater than 0, every time when PMF is greater than 0, then I will have a jump. Okay. And for this jump, the difference of that jump will be your PMF. So if the unit step has a jump at x, then the height of that jump will be the PMF. So that will be f of x minus f of x to the left. And then this x to the left is like taking the limit, and that h goes to 0. So if x does not jump, okay, then your CDF for the discrete case, it should stay as a constant. So it's like a stair, like a unit step. Okay, if there's no jump, it should stay as a constant. And then the unit step always has a solid dot on the left. and an empty dot on the right. So we call this right continuous. All right, so now that's just the properties of the discrete CDF. And we'll also mention about the mean. So for learning a new different type of random variables, we want to know their PMF, CDF, and their mean. Okay, the mean is that expected value. The expected value of a discrete random variable x is here. That means I consider all possible outcomes times their corresponding weightings. So the summation means all. And then this xk is the possible outcomes. Possible outcomes. And this PMF is the weighting. So I consider all possible outcomes times their corresponding weightings. That is your expected value. For example, I flip the coin 3 times, then what is the expected value of x? X could be like getting a head or getting a tail. So consider all possible outcomes. My possible outcomes of getting the heads is either 0, 1, 2, and 3, right? I can get 0 heads, 1 head, 2 heads, or 3 heads. Then times the corresponding weightings, that is the PMF. To get the 0 head, the PMF is 1/8. To get 1 head, the PMF is 3/8. Get 2 heads, 3/8. And get 3 heads, that'll be 1/8. So overall, you get 3/2. So 3/2 means that this is if we randomly flip the coin 3 times, on average, we have, on average, I'll put here, we'll have 1.5 heads. So let's see another example. I still flip the coin 3 times, but now the difference is that I have a rewards. If you get 2 heads, you get $1 back. 3 heads, you'll get $8. Or if you get 0 or only 1 head, then you get nothing. So to enter this game in the casino, you also need to pay $1.5 first. So the question will be that to bet or not to bet. Then we need to find the expected value. If you play that many times, will you earn money or you'll lose money? Okay. But how do we find the expected value? And also you need to ask yourself that expected value of what? So you need to define your random variable. Is that random variable just like heads or tail? But I also have a rewards here, right? So in this case, my random variable x is not the heads or tail. So that the x is the amount of rewards. Amount of rewards. Then the expected value x, I will consider all possible outcomes. So here, all possible outcomes. Now the random variable x is not defined as the heads or tail. Then what is the possible outcome? My random variable now is the amount of rewards, right? So my possible outcomes will be either 1, 8, or 0. So possible outcomes and times their corresponding weightings, which is the PMF. Okay, so my possible outcomes will be 1, 8, or 0. So to get their weightings, the PMF, I get 2 heads to get 1 buck. So 2 heads, the probability is 3/8. And then for 3 heads, my probability is 1/8. And for the 0 or 1 heads, my probability is 1/2. So overall, you get 11/8. And remember that you still need to pay the entrance fee. So the entrance fee is 1.5, which is 12/8. So and then your long-term overall rewards is 11/8. So eventually you will lose money because you get -1/8. That means on average you will lose. Right, so now let's see what is the mean or the expectation and also the sample mean. You probably will heard the sample mean before. So for the mean or expected value, it is a long-term average of the random variable x. But for the sample mean, let's see. If we conduct an experiment for n times, and then suppose we make an empirical observation of that xk is observed for nk times. Then this time for the average, then we can also calculate this average. And this average is sample mean. For the expected value is a long term, which means that it is like an infinite times. You'll get this value. But for sample mean, because it's impossible, right? Sometimes it is impractical. So then we have a sample mean. For example, like we want to know the average height of male in Taiwan, or the life expectancy in Taiwan. Then we will find maybe 10,000 people to find that mean. That is the sample mean. And in general, this sample mean will converge it to the expectation, the true mean. Okay, but they are not equal if I have a finite n. So now next, even though we haven't talked about the functions of random variables, but we just learned that first for the expected value of the function of random variables, because we'll use that a lot. If I have a function g, then the expectation of g of x. Also, for the expectation, we consider all possible function of outcomes times their corresponding weightings. They always need to consider all possible function of outcomes and then times their corresponding weightings. For example, why do we need to use this? Because sometimes it really depends on your function. Sometimes it is hard to find the PMF of your function. or sometimes, no, for this example, okay, z equals x squared. We know the PMF of x, but we probably don't know the PMF of z. Or the PMF of z is so expensive, so complicated, hard to express. But remember that when we find the expectation, we need the corresponding values, okay, that weightings. And that weighting is the PMF. So if you cannot find the PMF, or it is hard to find this PMF, then the other way, you can find the PMF of x. And this is like a function of z. So in this case, suppose my x, the PMF of x is -3, -1, 1, 3. So I have 1/4, 1/4, and they're all 1/4. And overall, you can see the summation of that will be 1. So it is a valid PMF. Now I want to find the expectation of z. According to the definition, I need to consider all possible outcomes zk times their corresponding weightings, which is the PMF of z. Okay, but for this PMF of z, as I said, that we probably don't know that, or it's really hard to calculate. Maybe okay, because like I don't know, or hard to calculate. The PMF of the random variable z. So what should we do? We know z equals x squared, so we can think about x squared. Z equals the x squared. And x squared, that is a function of random variables. And to find the mean, I also still consider all possible and outcomes. Here is the function of outcomes. And then times their corresponding weightings, which is the PMF of x. And in this case, I know my possible outcomes will be, my possible function of outcomes will be -3 squared, -1 squared, 1 squared, and 3 squared. 1 squared, -1 squared, one squared, and 3 squared. So their corresponding weightings, -3, my weighting, the PMF is 1/4. And also for -1, it is still 1/4. For 1, also 1/4. And for 3, it is also 1/4. So then I just sum those together, and you get 5. Now let's see some properties of this expectation. First, the linearity. For this linearity, if I want to find the expectation of two random variables, two functional random variables, then we can find their expectation individually and then do the summation. Because by the definition, expectation of gx plus h of x That means consider all possible outcomes, all possible function of outcomes. Here my outcomes will be h, g, and h function times their corresponding weightings. Their corresponding weightings, since they are the random variable x and is a function of x, so their weighting will be just the PMF of x. Then we can separate that. So for this summation, I have two parts. The first, I consider gxk times the PMF of xk of x, and also I sum another one that is function of h times the PMF of x. And now let's see the first term. What is the summation and g of x and times p of x? All possible function of outcomes times their corresponding weightings. So this is the expectation of g of x. So this is the expectation of g of x. And similarly, the second term, all possible function of outcomes times their corresponding weightings. So this is the expectation of h of x. Next one, if I have a scale, c times the random variable x, I can also put the c outside of the expectation. So similarly, if I calculate the expectation by the definition, I consider all possible outcomes, and here I also have a c. Possible outcomes times their corresponding weightings. And since c is just a constant, so I put it outside. And for this summation, you can see all possible outcomes, all of the possible outcomes, and the weightings. So again, for this summation, it is the expectation. And now, if I have a shift called DC shift, I plus a constant, then actually for the expectation, it doesn't matter. Well, it matters. It just, we still have my expectation, but we still plus this constant. So let's have a quick proof. So for the expectation, I still consider all possible outcomes, xk plus c, times their corresponding weightings, the PMF of x. This is, I also have two parts, xk times the PMF, and also c times the summation of PMF. Okay, so first, this part, all possible outcomes, their corresponding weightings, that is the expectation. How about the second part? What is the second part? I have a constant c, but at times, now I don't have possible outcomes, I only have PMF, and do the summation of the PMF. So what is this term? The properties of the PMF. So, right. So this overall is 1. And remember that we will use this property a lot. Okay, when we do some simplification or something else. So here, that's why we have a C. Now let's have an example. I want to find the expectation of 2x plus 10 squared. What is this expectation? First, we can take the perfect square out. Then we have 4x squared plus 40x plus 100. Now we can use the properties above. These three: linearity, scale, and the DC shift. All together, this is equal to for linearity. So I have a 4x squared, and then expectation of 40x, and also, oh, it's better to put it here. And also the DC shift, so it'll be 100. Then you'll get 4 and expectation of x squared, and 40 times the expectation of x plus 100. So you get 4 times 5, and also 40 times expectation of x plus 100. What is the expectation of x? They are all equal for their PMF. So this goes to 0. Then you get 120. Then the next one will be the variance and the moments. So let's see the first definition. The kth moment of a random variable means the expectation of x to the kth. So x squared means the second moment. And if I don't have square, if it is just e to the x, no. If it is the expectation of x, that is the first moment. Of your random variable x. And the variance of x will be sigma x squared. Okay, we subtract the mean and make it squared. So this is the formula. And then let's see the properties of the variance. Okay, so if we try to simplify the definition, then you'll get the variance will be the second moment minus the first moment squared. Okay. I think I missed the parenthesis. Okay, so now let's see the proof. Let's just simplify the definition. Okay, x minus the mean. So x minus mean, wow. X minus the mean squared. So if I take the perfect square out of, I have x squared minus 2x times the mean plus the expectation or the mean squared. From the linearity, we have the expectation of x squared minus, now remember that this, when we take the expectation, finally this is a number, okay? So it is a number. Then we only take, so if it is a number, it's like a constant, I can put it outside, okay? And then I take the mean, again, for this x. So that's why I have like a 2 times the mean times the mean. So 2 times the mean and times this expectation x minus the mean squared. So that is the second moment minus the first moment minus the first moment squared. Okay, the variance will be the second moment minus the first moment squared. If I have a constant, then the variance will become the constant squared times the variance. So again, we can use the definition. The variance is Cx, the variable, minus their mean squared. And you have the Cx and also minus the mean squared. That gives you C squared times the second moment minus C squared times the first moment squared. So that's why you get C squared variance. If I have a shift, the variance will be the same. So if I have a shift, that is the second moment square, the second moment minus the first moment squared. So you get x squared plus 2 times c times x plus c squared and minus c plus the mean square, and you get the second moment plus 2 times c times the mean plus c squared and minus c squared minus for the second part. For the second part, the last term will be the mean squared. Then you have the second moment minus the mean, the first moment squared. So it is still the variance of x. So now let's see an example finding the variance. Okay, I flip the coin 3 times, and I always need to define your random variable. Okay, so this time the random variable is the numbers of heads. And then the expectation we know is 3/2. Then what is the variance? Again, that you can plot the PMF. For the x, I have 0, 1, 2, and 3. And we get 1/8 for zeros. Get 3/8 for having 1 head, and also 2 heads, same value. But for the 3 heads, we will down back to 1/8. So here's 1/8, 3/8, 3/8, and 1/8. Then we need to find, because the variance is the second moment minus the first moment squared. We know the first moment, which is the mean. So now we need to find the second moment, x squared. So that means consider all possible outcomes squared times their corresponding weightings, the PMF of x. So all possible outcomes squared, that will be 0 squared, 1 squared, 2 squared, and 3 squared. And their possible corresponding weightings, 1/8, 3/8, 3/8, and also 1/8. And then I sum all this, we get 3. So the variance is the second moment minus the first moment squared, and that is 3/4. Okay, so today's last example. I flip one coin. Now it is not a fair coin. It's just like you can see here we have a probability P. So X is the outcome. X is 1 is P, and X is 0, that is 1 minus P. You can think about like 1 is like head or 0 is a tail. So how do we find the mean and variable? Oh, and also in this case, we have either 0 or 1. And the probability here, this is the PMF, okay? This is 1 over P, and this is P. So the expectation, consider all possible outcomes times their corresponding weightings. We have either 0 or 1. Their weightings is 1 minus P, and also P. So we just add all this together, and you get P. To find the variance, I need second moment, so I need x squared, okay, to find the expectation of x squared. Also consider all possible outcomes squared times their corresponding weightings. And here you have 0 squared and also 1 squared. The corresponding weightings is still 1 minus P and also P. So if you sum all this together, you will get P again. Then your variance will be the second moment minus the mean squared. Which is P minus P squared. You get P times 1 minus P.